you all for coming to our seminar. It's my pleasure to introduce Dr. Jere Lipps to talk to us today. Jere is currently with our very own Cooper Center. He's the director of the Cooper Center. Jere is a very well-known paleontologist. He got his bachelor's and PhD from UCLA, and I like him anyways.
I'm having a little trouble with you, Dave.
Yeah. I get that a lot. Jere did his bachelor's and PhD at UCLA, and then after that he went to UC Davis, where he was in the Department of Geology for a long time, including chair there. After Davis, he left to Berkeley in the Department of Integrative Biology, where he was eventually the chair, what do you call it, director of the Berkeley Museum?
Of Paleontology.
Paleontology?
And chair of the department and a lot of other stuff.
There you go.
A lot of extra work.
Yeah.
As you know.
As I know, yeah. And he has since come down, left that little school up in the Bay Area to join the powerhouse that is Cal State Fullerton, to be the director of the Cooper Center. And it's just a really great thing that they're doing at the Cooper Center. If you haven't had a chance to be there, I really encourage you a chance to hit Jere up for a tour to see some of the great stuff. I know a lot of you are actually students who are working out there as well. But I will turn it over to Jere to talk about something else that's near you to his heart, population, energy, and climate change. So,
thanks, Dave. So I need to declare, first of all, that this is my opinion, not the County of Orange's opinion. Because the Cooper Center is partners with the County of Orange and with Cal State Fullerton. So I kind of report to, I don't even know how many different bosses, but quite a few. And one of them might not appreciate everything I have to say here today in this particular environment. What I want to do, though, is to review for you a lot of information that relates to population, energy, and global change, and lay it out for you because it's more important to people than it is to me that you get with this and do something about it. And that's essentially my message to you today. And all geologists know that this is true, that civilization, especially those places like this one built on Newport Mesa, exist by geological consent. You couldn't have done that 125,000 years ago because it was covered up by the sea. We'll talk about that a bit. So what's the problem? Well, there's two problems. One of them is nature. We can blame a certain amount of this problem on nature, and the other is us. And I'll explain that. You can see here the disk of the sun, and the sun is, of course, our energy source and our heat source. So that's a very important element of climate change. And then the other element is us, and just fortunately, this airliner was caught going across the disk of the sun so that you can see it emitting all of this stuff from the background, from the rear end of it there. And so that's the sort of thing that we deal with in climate change. Let's look at what nature has done. This is the last 66 million years of geological time, and you can see this is a high latitude climate change diagram that starts, as I said, it's about 66 million years ago. It was almost 8 degrees C in the high latitudes. It goes up to a very high temperature in the same vicinity of 12 degrees centigrade this is. Remember, every degree centigrade gives you 9/5. You multiply it by 9/5 to get Fahrenheit. And then it starts declining a bit, and there are some peaks in here during the Miocene, and then it just crashes from about 14 million years to values that are lower than 0 centigrade. But that's because we have developed, in the last 14 million years, ice caps on each end of the globe. And so that changes the mechanism by which this is measured, which is the change in the value of an isotope of oxygen. No, I'll just hang in here. I'll be using this if I can make it go. Thanks. So, in the last 14, well, actually the last 30 million years or so, 35 million years, you can see over here the Antarctic began to develop ice sheets, mostly in the form of valley glaciers at first, and then later on becoming complete ice sheets over the entire continent. We have a good record of this in submarine cores taken offshore of Antarctica, and then finally hemispheric ice sheets in the northern hemisphere as well, covered, I'll show you, much of North America from Washington and New York north. And there's been a lot of variation. So we've been trending towards this refrigeration of the Earth, if you will, and we live in that time. And here's a longer, more detailed presentation for the last 780,000 years. And this is the natural variation caused by the relationship of the sun to the Earth. In other words, the Earth changes its distance from the sun depending on the shape of the orbit, the tilt, and where the equinoxes are on its Earth's trip around the sun. Incidentally, there was a scientific literacy exam, I have to tell you about this because I kind of like it, where they surveyed 205 randomly selected Americans over the age of 21, and they asked them, how long does it take the Earth to go around the sun? 1 day, 1 week, 1 month, or 1 year? How many of you think 1 year? Okay, all the rest of you are wrong. But that's not the funny part. 15% of the people said there was no right answer because the sun goes around the Earth. So they just left the question blank. But let me assure you, we go around the sun, and depending on the tilt of the orbit and where the equinoxes are, we can get this kind of a curve. This is a combination of these things which have different time intervals on the order of 23 to 110,000 years. And when you put it all together, it gives you this kind of a curve, which is also the climate curve. So you can see that the points at the top are the interglacials, and this last one over here is the one in which we live, and we live right there on that tip. The last time we had an interglacial like that was 125,000 years ago, and at that time it was a little bit warmer on the average, and sea levels, because warmth causes the ice to melt, was about 8 meters, 27 feet or so higher than it is today. And then it fell, as you come from 125,000 years ago, it fell down slowly. You can see sort of it leaps and bounds down to low temperatures in a glacial period of time and sea level, because you're stacking water from the sea onto the continents as ice. Sea level goes down. It was down almost 400 feet lower than it is today, 120 some odd meters. And this is a repeating kind of thing, and that's what nature does. This orbit, tilt, and equinox is called the Milankovitch cycles, are very slight changes to the input of the solar radiation to the Earth. So everything has to be aligned perfectly to get the Milankovitch cycles to do this in such an extreme way. That'll be important here in a moment. So let's look at temperature and carbon dioxide variation over the last 420,000 years. And the blue line is temperature, and you've just seen that. You can see here's the 125 high peak that we mentioned. But we're also interested in carbon dioxide. That's a naturally occurring gas in the atmosphere, and we also make it. This is the way it was before we started making it. And you can notice that the values of CO2 over here on the left-hand side seldom went above 280 parts per million. Once, right there, it went a little bit over 300. This is due, these peaks and valleys of CO2 is due to, as you warm up the oceans, CO2 is released from the oceans, and also from permafrost and other things that, where you can get it out of the permafrost or whatever it's in, and back into the atmosphere. And it never went above about 280 parts per million. And this is what it was like during the glacial period, the last glacial. You can see how the ice cover North America down here, because all that ice in North America and Eurasian came from the water in the sea. Sea level dropped, and the Beringia, the land bridge between Asia and North America, opened up, and people came across. That was about 18 to 13,000 years ago. So the oldest people we know of in North America are about 12,500 years old. We're hoping to find some right here in Orange County. Our record goes back 10,000 years as far as people are concerned. So how did this fluctuation of sea level and temperature affect places that we're familiar with, like San Francisco Bay, which is a very shallow, ephemeral estuary? And this is how it affected it. Here's the last 125,000 years, with the fives peaking, one peak above sea level, 8 meters, 5E, and then the rest of them coming down like that. The red line is the line at which San Francisco becomes a bay. This is the 18-meter point. All the other times below the line, San Francisco was a river valley, and the shore was 30 miles off the Golden Gate when it was down at 120 meters or so. So the way that looks is, here's the 120 meter or 20,000 to 13,000 year old shoreline right out there. There's the Farallon Islands. You can see they're about 27 miles out, and then it's 3 more miles out to the edge of the shoreline there. And then 10,000 years ago, sea level rose up to the present day coastline, more or less, and it began to intrude into San Francisco Bay by the present day shoreline. I don't mean it was at that elevation, but because this is a cliff coastline, it was right at about that level. You can see how it entered into the bay just a little bit. And then this lighter blue, 8,000 years ago, the bay began to fill up. And it wasn't until 4,000 years ago, this lighter blue, that we actually had a bay that we could call San Francisco Bay. Prior to that, it was a river valley or just a big estuary. And people were living alongside of this estuary during this entire time. They had lived out here 13,000 years ago, and then as they moved backwards with the shoreline, they began to build these big mounds of shells as they tried to make a living off the bay. And 125 years ago, you can see the very lightest blue. That's the way the bay was when Europeans came and started messing it up. Most of this shoreline was marsh. Nowadays, there's about 10% of the original marsh left around San Francisco Bay, and it has retreated back considerably, so that there's a lot of marsh missing. You could say the same story for Orange County. Here's the 13,000-year shoreline, and you can see here's Newport Bay. That used to be a river valley, and it emptied out here someplace. These other estuaries were probably rivers also that emptied out to places far out. Now, when humans came here, they may have lived out here, but after the sea came up to somewhere in this vicinity, they built big, huge middens here, and at Bolsa Chica, Dana Point, and a few other places along the coast. So you get the same story, but it's not as clear as it is in San Francisco because of the nature of the coast and the fact that we pretty much cemented all this over and can't see a lot of the stuff with light. That's both good and bad. So that's nature. What about us? Well, there's 3 things that are really important that we're doing. Population, energy, and global warming. They're all related. And then we're also doing a lot of other things, of which habitat destruction, markets, and a whole bunch of other things are all related to these problems of climate change. This is the world population. Let me see. Jere, when you were born, how many billion people were there on Earth?
Not even 1.
So you're about 100 years old.
I think so.
When I was born, there was about a little over 2 billion people on Earth. How about you?
About 2.75.
2.75 billion people when Brady was born. Susie, you must be about 2.5, huh? Anyway, and the rest of you, how about you and you? When were you born?
80s.
In the 80s? 4.5 billion.
93.
So 5 billion, 5+ billion. We are now at over 7 billion. So we've come 5 billion people in the lifespans of some of the people in this room. That's incredible. In fact, we've known about this problem for decades. Do you remember that book, The Population Bomb, written in 1968? He predicted in that book all the things that are going on. We got very upset back in the 60s about that, about climate change, and we didn't do a damn thing about it. We just continued this projection. And this is affecting businesses right here in Orange County. I was at a business forum. They took me there. Not the place I ordinarily would go, but they thought maybe I could do some good for the Cooper Center by talking to business people. I don't speak their language, is what I discovered. But the lady in charge, the president of the thing, was talking about the population in Orange County and how it had gone from a couple 100,000 since she had been there to 3.2, she said, million people. Actually, she's wrong, it's 3.1, but not much. And her conclusion was, you people have to stop having sex. And that really disturbed all those people in that room. They said, no, you're wrong. We can still do that, but we have to stop reproducing. Yeah, right. So, Paul Ehrlich, who wrote the book, Population Bomb, continues to write about this stuff. And all I can say about it is an increasing thing, although the rate of increase is lowering. So it's taking more time to get to the next billion, but you can see there's not much time difference between these things. And where we're going, 9 billion people on this chart, some of you in this room will be living then, and your children and your grandchildren will likely see 12 billion. I think that's scary. So the real problem underlying everything is a world full of people. This is how many people there were on Earth yesterday. There were 7,758,682. I know that's true because I got it from the U.S. Census. And this is their projection for 2050, just less than 40 years from now. So many of you in this room will see 9,400,000,000 people on Earth. That's a lot. And what about the United States? In 2050, there will be almost 400 million people in the United States. Right now, there's 315 million people in the United States. Still, it's a little hard for us to relate to any of those numbers. So how about California? We'll have 50 million people in 2050. And if you think the freeways are bad today, wait till you see it in 2050. All I can say is it's a good thing Orange County is only a few decades old and the freeways are 6 or 7 lanes wide. In the Bay Area, there will not be any room for anybody to go anywhere. So there's a big problem here that we have to work on. Orange County, which has 3.1 million people right now, will have close to 4 million people perhaps. The projections are kind of hard for me to dig out on that one. Where they're all going to go, I don't know. There is a mass migration out of Orange County, according to the Business Forum people who said their children couldn't find a house in Orange County that they could afford to buy, so they were all moving to Alabama. Tuscaloosa, where the houses last for a couple decades before the tornadoes knock them down. So this is in your kid's lifetime. If you're going to have kids, you've got something to worry about, I think. There's going to be a lot of people doing a lot of stuff, like driving, like getting to the stores and in the schools and lots of other things, and it's going to be a big problem if people don't plan carefully. And in order to plan carefully, you have to think according to what's real. You cannot say, I don't believe in reality, as many people do, right here in Orange County even. Here's the vital statistics, the rate at which the population in the world is growing. Every second, it increases 2.4 people. In a minute, there's 145 new people. In a month, 6,369,000 are increased, the population of the world. And each year, 76 million. Based on what was happening in 2011, if the rate picks up, these numbers would go up. If it declines, it would go down.
Did you reverse those numbers?
Pardon?
You said 2.4, did you mean, oh, I see, 2.4 over here.
2.4 people.
Okay.
Some of you are going to have to get sliced up. So, again, follow the lady's advice at the business forum. Stop. So here's some of the human developments in the years past. 150,000 years ago or so, Homo sapiens became somewhat abundant in Africa and began to spread across Europe and Asia. And 10,000 years ago, this is more interesting, agriculture began. At the same time, people were burning the landscape and clearing the land in order to do that. And there's at least one person out there who has the hypothesis that because our current interglacial peak has lasted 10,000 years, which is about 5,000 to 6,000 years longer than the previous ones, that this initial agricultural burning and clearance of the land has caused global warming, even back then, 10,000 years ago. And it has contributed to holding the climate stable by generating CO2 by burning all of that organic material. And then industrialization began 150 years or so ago, and coal was burned for fuel and to power all of that industry. Again, more emissions into the atmosphere. And 100 years ago, we could begin to see significant increase in global warming and CO2 emissions. And 120 years ago, oil production really began in earnest. Oil had been used and found even in California before that, but it really began in earnest. So we're looking at the last 125, 150 years ago for the explanation for a lot of this stuff. So let's just look one more time at the last interglacial, about 125,000 years ago, when sea level was 27 or so feet higher than it is today. And this slide is one that I used to use in my Geology 1 class 4 decades ago. We knew about this stuff. We knew all about this. We knew all about the population stuff, but we didn't do anything. You have my apologies, but that's about all I can give you. We should have done something. So, you can see that same pattern. Here's the beginnings of agriculture. Here's the present interglacial, and normally it would have gone back down by the constraints of the Milankovitch cycle into another glaciation. But because of the carbon dioxide-induced superinterglacial, as they called it then, not global warming especially, it took off like that, and then in the 70s we thought it would go back down. But by careful analysis of that point and the amount of energy required to get past the Milankovitch cycles, which are not really a very strong thing, we have so much global warming now, probably we will not go back into an interglacial period. That's at least one climatologist's point of view. And I guess that's worrisome. So let's take a look at one of the causes, energy. And most of our energy in this country, or in California anyway, we're concerned mostly about oil. But the whole country's concerned about it. And it's a non-renewable resource. And it's a scarce resource in many ways. You need to have, in the past, the geologic past, millions of years ago, the right primary productivity of the right phytoplankton that live in the oceans, that are deposited in the right environments, anoxic ones, those without oxygen, that would destroy the organic molecules that these things are made out of. And then they have to be, in that environment, heated up through what's called the oil window, certain temperature range. So as they get buried under the sediment, they pass through that window. If they go all the way through it, it gets too hot, and all the organic molecules break up, and you lose the oil. So it's got to get to a certain temperature, and it can't go too far. And then that oil has to migrate to some place where you can find it, where it's trapped, and then where you can, as I say, find it, discover it, and then finally you have to produce it. So there's 7 steps. That's why geology is so fascinating for the oil company people. These are geologists who go out there and they test their hypotheses. Most of us don't get to test them. But these guys, the test is they found oil when they drilled it. So let's just take a look at this. So 90% of the oil migrates out of the ground and is lost. Like at the La Brea tar pits, McKittrick, Carpinteria, even Brea right up here. You can go up there and see tar seeps where the oil is seeping out of the ground. Production is difficult. This is the Curtin River field. It's pumping oil out of rocks that the oil is migrated into from another formation, and you can see in the background steam plants that are generating steam, and they pump it down one well over there, and they push it through the sedimentary rock and warm it up, and under pressure, push it to a well where they can drill it or extract it. In a way, that's like fracking. In fact, they have been doing fracking in California for several decades, but never called it that word. It didn't exist in the old days. So these are the world's oil resources. Conventional oil, we know how to get that. Heavy oil, extra heavy oil, and oil sands, that's difficult. You got to mine it. You can't pump it. So what's been going on in Canada, for example, is that they're mining the oil shales and oil sands and then extracting the oil from that. And fracking does the same thing. And I'll show you that in the next slide. This is National Geographic from this month. So this is the latest word. America strikes oil. And it's all about the Bakken Shale, which is a Devonian Mississippian age oil shale in North Dakota and Montana. And they estimate that it contains 10 to 12 billion barrels of oil. That's crude oil. The Marcellus Shale, another Devonian formation, has 3.4 billion barrels of oil, and that's in West Virginia, Pennsylvania, and New York. And the Eagle Ford Shale and Cretaceous rocks in Texas, 3 billion barrels. The big one here is the Monterey Shale, right here in California. It's Miocene in age, and they estimate, one guy says 15 billion barrels. The top guy says 300 billion barrels of oil in the Monterey Shale. So there are a number of small companies that are taking out leases. Some of them own 300,000 acres of lease in areas on the west side of the valley and the coast ranges in Monterey Shale territory where they're going to start fracking. The interesting thing about this is that the Chevron company, which has been drilling in the Miocene Monterey Formation for decades and decades, is not interested in doing this. So there's some geological reason, probably the faulting and breaking and folding that this formation undergoes in California, that these formations, which are relatively flat, don't undergo. So it's a tough job. We'll talk about that more in a minute. This is out of the National Geographic too. This shows how you do fracking. You drill a well 13,000 or 10,000 feet deep, and then you whipstock it off so that it goes horizontal, and you drill it now for 2 to 5 miles through the shale unit that you want to drill. And then you release various fluids, water, steam, acids, all kinds of other chemicals that will loosen up the rock and you put it under pressure so that you crack it open. So that's where some of the fracking part of that word comes from. You're actually trying to crack the formation and get the oil out of these tight shales. And each one of these dots is a well, and the line going off of the well is the horizontal. The Monterey Shale occurs in Orange County. Here's a place where you can actually go see it in Back Bay in Newport. You can drive along Back Bay. It's one way in this direction. And stop there and look at that formation. It's a diatomaceous. In other words, it's made of diatoms. Anybody know what diatoms are made of? Silica. Pardon?
Glass.
Yep, glass. So what kind of a fluid do you think they're talking about fracking the Monterey with? Hydrofluoric acid. One of the worst acids you can possibly encounter in your life. And that's what they're talking about using, because it's made of silica mostly. On the other hand, there's also a lot of calcium carbonate in there in the form of different kinds of fossils. And one of the things that HF does to calcium carbonate is that it replaces the carbonate part of that with fluoride, and calcium fluoride is insoluble. So they may well be cementing up some of their holes that they intend to frack. We'll see how this goes. It's very interesting. And we ought to all watch it, because it could happen. Probably not there underneath the, what's that big shopping center? Fashion Island. Probably that won't happen. But maybe in the Bakken Formation in North Dakota, if you buy a piece of land there, you own the surface rights, but not the mineral rights. So a company can come in, set up a well, and then drill under your property and get the oil out underneath your property. So what I do is, as far as Fashion Island is, I just start drilling right here like that, get the oil out from under that place, leave my HF behind. So the real question is, how does this affect our view of the future of oil? And M. King Hubbard, back in 1958, came up with the idea of peak oil. And peak oil is when you produce oil and you continue to produce more and more oil, and then you can't find any more and you can't produce it, and you go over the hill like this, and you're not finding any new oil, so you're using up the old oil until there isn't any left. And that peak is called peak oil. It's become a useful word in non-renewable resources in general. So he predicted, he worked for the Shell Oil Company at the time, and he predicted that peak oil in the United States would run out in 1976, if I recall right, and Shell tried to fire him. He managed to hang on to his job and get a better job at a university. So there's a lot of argument about this. This is the lowering in production due to the Saudi Arabia and OPEC embargo on oil. So there are some events that affect this. One of the events that doesn't seem to affect it very much is new discoveries. Because we hit all the big discoveries. And the big question then, are all these fracking environments going to change this curve? The way they would change it would be to shove this out farther so that we'd have oil longer. Most people don't think that will happen, but we don't know for sure. In any case, sooner or later we'll run out of oil. And that's true for other non-renewable resources that are very important to us, like phosphate. We use that for fertilizer and all sorts of other things. And it'll hit its peak in 30 years. And coal, which has maybe 300 years to its peak. And then we'll be on the downside of that. This diagram, which comes from a petroleum geologist, he predicted or stated that the peak was Thanksgiving Day, 2005. And we've been on the downside of that hill ever since. This means that the price of oil will just go up. Soon we'll be, well, what were we a couple weeks ago? $4.50 a gallon or something like that. Close to $5 in some places. In Europe, it's $8 to $11. We'll be there soon. So what about coal? I haven't really addressed coal because it's such an enormous problem. And most of our generation of oil, energy is by coal-fired plants, power plants in the United States. So when I had the opportunity to visit this place in Germany, which is a coal mining place, I took it up. And here it's totally automated. And you can see this big machine there It's driven by one person. It's huge. You can see down in this lower picture over here, a human doesn't even come up to that part right there. This building is 30 stories, I mean this thing is 30 stories high just in this part of the thing. And it has out on this arm a big round thing that rips up the coal. It's actually lignite, comes up this ramp, and then it gets broken up into smaller pieces, goes up this ramp where it's dropped onto a conveyor belt right there. That's the conveyor belt. And that conveyor belt takes it to one of 3 power plants at the other end of the mine. And they generate the energy right there, as close to the mine as they can be. And they've already condemned all the roads around because this mine supplies about a third of Germany and some of France in terms of their electrical power. And it runs 24 hours a day, 365 days a year. So what is global warming? Well, you guys know it's all about certain gases in the atmosphere that trap heat. But let's look at it a little bit more broadly than that. Venus, Earth, and Mars are all greenhouse planets. And you'll see some interesting differences here in a moment. These gases in the atmosphere then trap heat. This is just a matter of thermodynamics. It's nothing that we're inventing here. It's a fact. These gases are contributed by humans. They're also contributed by natural processes like volcanoes and methane gas that's being released from the seafloor. And it's happening now at a rate that's so fast that nature can't remove it fast enough. So it's accumulating in the atmosphere. That's why we saw CO2 going up. And it accumulates in the atmosphere, which then warms the oceans. They're linked, and both of them warm. And that's the problem. So these are the greenhouse gases, and the 2 that are most important to us are carbon dioxide and methane. Carbon dioxide is a long-lasting gas. Once it gets into the atmosphere, it stays there naturally for hundreds of years. Methane is about 21 or 22 times better greenhouse, more effective greenhouse gas than CO2. Where do we get methane into our atmosphere? Some of it comes naturally. Cow farts are a big producer of methane. All those hamburgers that go to McDonald's have been made and generated partly by making methane too. And that's a very powerful greenhouse gas. Methane, it turns out, freezes at a certain low temperature under pressure, so that at water depths of about 600 meters, there are lots of these methane ices, they call them clathrates, frozen in the seafloor and also in the Arctic Ocean. And as the ocean warms up, the methane gas is released, sometimes explosively. And we see it happening in the Arctic Ocean today. There are oceanographers out there measuring the amount of methane that's bubbling up from the seafloor today. I know some of them. So those are the 2 biggies. And they both are big problems. Here's carbon dioxide on Venus. 96% of Venus' atmosphere is CO2. It's a super greenhouse. The surface temperature of Venus is like 700 degrees. On Mars, it's 95%. Venus is closer to the sun, and it's the same size as Earth. Mars is a quarter the size of Earth, and it's further from the sun, and it can't hold its atmosphere. It's 100th that of Earth. So 95% of it being carbon dioxide doesn't do much in terms of warming that atmosphere because it's so small. And so the surface temperature on Mars is an average 60 or 61 C, minus 60 or 61 C. On Earth, we have less than a percentage of carbon dioxide. So why is that? Like tectonics, goes back to geology. So as CO2 is produced naturally by volcanoes, and to some extent by what we do, the process of sedimentation, making inorganic calcium carbonate, and biogenic carbonate, that is shells of organisms that have calcium carbonate shells, they settle out to the sea floor, and they have trapped in the molecules of their calcium carbonate shells CO2. So it gets trapped in their shells, and it stays there until those shells get subducted down an oceanic plate underneath the continent. And then when it melts down here, it gets re-released into the atmosphere as CO2 gas. This is a process that can take hundreds of millions of years. So that's what has been keeping our atmosphere at such a low temperature and low amounts of CO2. If we were, if this didn't happen, we'd be like Venus, and we wouldn't be here. So these are the carbon loops. So there's this atmosphere terrestrial cycle. The fuels burn up, make CO2, that gets transferred to the terrestrial biosphere, and some of that goes back to the atmosphere. Same with the ocean, and then through plate tectonics, it gets hooked up with the geosphere and sequestered in the structure of the oceanic and continental plates. So this is what CO2 looks like for the last 400,000 years. And you can see, as I said, most of it's 280 or so, one little peak there up into 300 parts per million, and that's natural. That's being controlled by these natural processes. What happens when humans begin to introduce their things? Here we are back 150 years ago when industrialization began, and you can see CO2 begins to creep up well above the 300 or 280 mark that was the natural level. And now it's gone up on this chart to about 370, let's say. I want to show you where we are today. But before I do that, this is a correlation between the global population and the amount of CO2 released into the atmosphere and the numbers of parts per million. And you can see how this has gone up. So when the population was 2.8 billion, it was about 310 parts per million. As it goes up to 330 parts per million, it's 3.8 billion. Today, it's 7 billion people, and we're at 396 parts per billion. That is 1/3 higher than it's ever been in the last 2 million years or so. So what does this mean then? What are the greenhouse effects that come from this? Well, increasing CO2, which I want to talk about in a minute, increasing temperature and sea level rise. And all these other things on this chart also happen, and others that aren't on the chart. But I'm only going to talk about those three. This is this February's record from Mauna Loa, where they measure CO2, which is sort of a measure of the northern hemisphere. And you can see on this chart that we are now at 396.8 parts per million up here at that point. The red lines are the the seasonal fluctuation in CO2, chiefly produced by photosynthesis. So plants, when they start photosynthesizing in the spring and summer, release more CO2 and it gets used up. But on the average, it's creeping up. So in 2014, we will reach 400 parts per million, and I think we should have a party. Or maybe a wake. There are people, Jim Hansen, for example, who said that when we hit 450, the game is over. And by that he meant we've lost it. He's now retreated to 350, and we're 50 parts per million above that prediction. So I kind of agree with him. I think that maybe we should start planning for a really hot climate and a lot of other things because we've lost it. We don't seem to have on the table a way to sequester the carbon dioxide that's in the atmosphere and say pump it down into the Earth's subsurface or into the oceans where it would be stable for a while anyway. Instead, people say, well, buy a tree, plant a tree. Yes, that'll use up a little carbon dioxide, but don't ever kill that tree because that will release it back into the atmosphere. This is the land surface average temperature. I love this chart, I'll tell you why. Because it was produced by this Berkeley Earth Group, which is run by Rich Muller, a physicist at Berkeley, and he was a great climate skeptic. He wrote blogs on this just 4 years ago about how climate change was a hoax, it was crazy, it didn't mean anything. So he got his group together and they got 36,000 surface temperature measurements, analyzed them, and got this graph, and he has now concluded that yes, the globe is warming and humans are a cause with volcanoes a secondary cause. So that's why I show you this, that even a climate skeptic joined us because he's a good scientist. He may be a lot of things, and he's certainly a skeptic when it comes to a lot of things. He was big on the asteroid impact that killed the dinosaurs, for example. But he was for it. I'm against it. So I was pleased to be able to say that I think he's a great scientist because it changed his mind about a really important thing that he'd already written about in a negative way. So what does all this do for us? Besides increasing population, we're going to warm a lot, sea level will rise, destruction of moving of nearshore facilities and beaches will be required. In fact, there won't be beaches, there won't be any people like this sitting on the beach because the beach will be washed away. Increased warming through El Niños, acidification of the oceans, and a whole bunch of other things that will impact us in California. This shows the heat. Maybe you can't read this, but the dark red is 7.3 Fahrenheit, and the lighter colors are 7.8 increases in Fahrenheit increases. And you'll notice that the coast is always cool. That's because the California current comes down from higher latitudes, bringing cold water along the coast and keeps that cool. But out in the valley, Bakersfield, can they stand another 7 degrees in the summertime? It's already 120. Fresno, same deal. I remember working in Fresno doing geology. I'd get up at 3 in the morning because it was already 110 degrees after breakfast normally. As soon as the sun came up, we had to go back. So these poor suckers, excuse me, my friends at Cal State Fresno, about 7 degrees higher. And this is interesting. This is my own interpretation based on watching hurricanes. This shows the North American West Coast from Washington down to Puerto Vallarta down here. And the California current comes down like this. It's a cold current coming out of the Gulf of Alaska. Comes down and at point conception it moves offshore because the shoreline goes that way. But it still is controlling the temperature all the way down to Cabo San Lucas at the tip of Baja California. And it's a cool upwelling current. It stays cool all the way down because there's upwelling of cool water. So when you get a hurricane developing off Baja California in this area, they almost always go up the Gulf on that side of Baja California because that's where the warm water is and they track warm water. However, every once in a while, one will go outside of Baja and continue up the coast all the way to, in fact, off San Francisco. And I'll show you one. This is Hurricane Javier in 2004. Here it is off Baja California. And this one traveled up the west side of Baja California. And by the time it got to San Francisco, it was just producing thunderclouds and rain. But it did go off this way. What happens when the ocean warms off this coast? Are we going to get a series of hurricanes through Southern California? Don't know. But this kind of scenario, based on Javier, suggests it's something we should be aware of. I haven't ever heard anybody talk about hurricanes off California. Maybe some of you have. So what about ice and the potential sea level rise? Here's the ice accumulated on different parts of the world. Here's all the other ice. These are glaciers. There's 0.45 meters of ice stored there. Greenland, 6.5 meters. The Antarctic Peninsula and West Antarctica add up to about 8.5 meters. and East Antarctica is 64, 65 meters of sea level rise stored in their ice. So if you melt the ice on the continent, sea level will rise that much. So these are melting glaciers. Here's Glacier San Rafael in Chile, where I had the opportunity to watch the measure of the retreat of this glacier. In 9 years, it went from here to there. That's over 100 meters. And if you look carefully along here, you can see where the glacier was. Came up like that. And then above that is another level where plants have only just recently begun to grow back, where the glacier had stripped them off. And all of this within historic times. Darwin sailed by this and said that these glaciers were extending out into the sea. Now they're halfway back up to the ice cap on that part of South America, and we give that glacier another 30 years before it's entirely gone. Maybe less at the rate things are going. Same with Greenland. Here's just a 10-year melt extent, mostly around the margins to 2002. And you probably saw the story about how the central part of Greenland has been melting more recently. And then this is Antarctica. This is 1.5 times as big as the United States. It's a huge volume. It's a huge place. And it's divided into 2 parts. West Antarctica, where these big ice shelves, starting with the Larsen Ice Shelf, the Ronnie Ice Shelf, here's the Ross Ice Shelf. Those are the big ones. And they're falling apart. Larsen is already broken up. The Wilkins ice cap, or ice shelf, broke away. The Pine Island one is going right now. And they're collapsing. These ice shelves buffer, what's the word I'm looking for? Buttress the ice that's on land. And this ice is very high. At the center part of Antarctica, where the South Pole is, 13,000 feet above the base. And where the line, where the colors are red, the ice is moving very fast. Where it's blue, it's not moving hardly at all. East Antarctica is not moving very much, but West Antarctica is. And if West Antarctica all of a sudden slipped off, or collapsed, or disintegrated, it would raise sea level, as I said, 8.5 meters. Another reason for that is this shows the sub-ice topography. Everything in blue is below sea level now. It would rise above sea level probably once the ice was removed through isostatic rebound of the crust, but that takes many years. So once the water gets under the ice in West Antarctica, it will tend to cause the ice to melt from below. Because it turns out that the ocean waters at these levels are much warmer than they used to be. So warm that we're now getting crabs in Antarctica where we never had crabs for 45 million years. So how many people would be impacted by the 1.5 meters that people have predicted and accepted by 2100? 440,000. But of course it doesn't rise in one big chunk, it rises gradually over some period of time, so that in 2050, 250,000 people will be affected, and maybe with a 10-foot rise, 1 million people in 2100. This shows the inundation of Orange County with this 1.4 meter sea level rise that's predicted by 2100. That's based mainly on the thermal expansion of the oceans as they warm up, and some ice that's being shed to the oceans today. And that's what it would do here. In fact, they're planning on how to deal with that. But what if the ice caps collapsed into the ocean? Would Orange County be ready for an 8-meter rise in sea level? That's a rough estimate of where that inundation would take place. And what about a 15-meter or 50 feet if West Antarctica and Greenland both went? East Antarctica is not going to go for probably 300 years, so we'll let our great-grandkids worry about that one. Anyway, this happens worldwide too. This shows that Orange County is the 3rd largest impacted county in California by that sea level rise. The others are Alameda and San Mateo, and this 4.7-foot rise in sea level will cause damage to 540 miles of highways, And it'll cost about $17 billion in today's dollars to deal with that problem. This is information put together by the Pacific Institute. Here's San Francisco Bay. Now and in 30 years, you can see over here is the San Francisco airport. I have to work this thing backwards. There's the airport right there. And if you look in the same place, with a very tiny rise in sea level, they're about a meter above the airport sea level, it'll be inundated. So San Francisco Bay Area governments have had contests about what to do with a 1.5 meter rise in sea level, and they give prizes for people who come up with good suggestions. Or perhaps we could do like North Carolina did, and essentially outlaw sea level rise. So that's what their legislature did. They said that you can only use estimates from the year 1900 on, and you can't change the rate. I mean, this is total blindness. And fortunately, some of the best people, like the author of this book on global climate change, live in North Carolina, and they have convinced the Assembly at least to stop this for 4 years. At least in California, we have had a governor, Schwarzenegger, who put all of this stuff into place. Our rules on sea level rises expect 1.5 meters, but plan for even more than that, depending on the conditions. So we've been pretty good about it. So here's the rates. Humans have effects over hundreds of years. Sudden release of these methane collapse rates or catastrophic collapse of ice can happen in tens of years. Some places look like they might even have the beginnings of it soon. So in your kid's lifetime, this is what's going to happen. The world's population will increase by 3 billion. US by 50 million to 400 million people. Petroleum will be used up. We'll have to think of something else. Climate will warm, not just several degrees, actually between 8 and 12 degrees, because when we talk about the average increase in temperature, it's always the average from the entire globe. But the tropics are not warming as fast as the high latitudes, so you have to make up for that 2 degrees average by increasing the averages in the high latitudes. And where it's happening fastest today is the Antarctic Peninsula and Alaska, both at about the same latitudes in high latitude seas. Because CO2 dissolves into the oceans, they will become weakly acidic, perhaps. Hurricanes may not become more numerous, but they will grow in intensity as the sea warms, because that changes things. And we already see biodiversity changes in both marine and terrestrial biotas. So only you can really help turn this around, and your children. So personally, this is the way you're already being impacted. Food production and costs are going up because of transportation costs, because of fertilizer, because of global warming, and things are changing. For example, and you know, these companies that are doing it, they know all about this. So that, for example, seed companies, they want you to buy their seeds. So on the back where they have their little temperature map of when you can plant your seeds, they've changed that. You can plant things earlier now, even in the far northerly areas, because spring comes earlier. It's warmer, it's hotter, and they want you to buy their seeds, so they're telling you the truth. On the other hand, Exxon knows all about this, so does Chevron. They've got some of the best geoscientists in the world, and certainly the biggest computer systems to do all this other stuff with. They know what's going on, and they're planning on drilling the Arctic when there's no ice, and they know about when that'll happen, so they're preparing for it. They're preparing for the Northwest Passage to be open as the Arctic ice disappears. And they're planning a lot of things. Look at British Petroleum, BP. They changed their name from British Petroleum to Beyond Petroleum because they know that petroleum is a risky business, and they are countering it on their quarterly annual report basis by advertising on television that we got more oil and we know what to do with, buy more gas and all that stuff, increase our profits. But they know about it. It's going to be hotter here, earlier springs, less water, so it'll be drier, more drought, Texas, Colorado, all those places. Pollen allergies earlier and more intense, I just found that out. I just found that out this morning. So here's the map that was released last week for pollen. You can see the highest rates of pollen like this. And the explanation for this increase was global warming. And we all know about fires, and I hear that Orange County will have a lot of fires this coming summer, according to the news this morning. California in general will. So that hazard will increase because the air's drier. There's not so much water around. So let me just skip those comments and give you 10 things you can do now. The questions I had there before are from the deniers of climate change, and they just have to look at the facts and they should change their minds. So tell your friends, use Facebook and Twitter, learn about these problems so that you can explain it to your friends, and then you can volunteer to help join various organizations, and you can work with various organizations all the way from national through local governments. And I especially urge you to write to policymakers, officials, and yes, the politicians. Write to them. Some of them believe in climate change, some of them don't. And then cut your own carbon footprint. And then the 10th one is to promote alternative energy sources carefully. You've all probably seen this out along I-10. This is Moronga Valley, which is now filled up with wind farms to generate electricity for, I understand, about 300,000 homes. I am just absolutely opposed to this. They have ruined the desert. That's my value. Is the natural desert view was beautiful, and now it's all cluttered up with these windmills, some of which don't even work. Another thing you can do is let's have a celebration of some sort. Dave Bowman runs in part this shakeout day where we all practice when big earthquake comes, the big one. We can do the same thing with climate change. We can have the Great American Fix the Climate Day. We can have festivals with things like this, and especially activities where we can have lecture series in the park. We can have things going on for the kids. We can involve all sorts of people. Here's some Native Americans doing the same thing. And then we can enlist the help of some of our greatest outreach people, like Professor Bowman, to do this work for us. Thanks very much.